Hi, I'm Nishant.
Hi, I'm Senith Silva.
My name is Tehan, and we will be going through the presentation of our ECE 4179 project, which is segmentation and styling of clothing apparel using neural networks. So the proposed project we are currently working on is a neural network-based mobile app that caters to the fashion industry, which has been expanded towards digital platforms. The main goal is to create an interface for fashion designers that promotes flexibility and creativity. So before we get into the technical details of how that works, let's take a look at what the app actually does. And the best way to do this is by a conceptual video. So let's get to it. So what you have seen is a few of the many neural network-based functionalities implemented. So far, our focus on this project is the clothing segmentation and style transferring functionality, which we will go through in this presentation. So let's get into the details of how we achieve this. So the overall approach is the designer inputs an image of a clothing apparel, which is segmented out from the background, and that clothing can be styled in different ways using the desired style. The input image should only contain one piece of clothing at a time. However, this functionality was later improved to include images of people wearing clothes as well. This is due to the nature of the data sets we use, which we will get into later on. A neural model consisting of CNNs is used to extract the style from the desired style image and backpropagate that information onto the clothing image where the merging and blending of the style takes place. The control over the level of detail and strength of transfer is what makes the application unique and more flexible for designers, which is controlled by different hyperparameters of the neural network. The output of the application would be the clothing item style according to the user's desire and the background remaining as it was, which is achieved using a unit-based segmentation architecture. Now, the method used for neural style transfer consists of a technique using three images: one content image, one style image, and the target output image. This target image is a randomly initialized matrix and is endowed with a gradient parameter, which transforms the target image into a blend of the content and style image. The loss function used to achieve this has two components. Firstly, to match the pixel level features from the content image, we use the mean squared error loss between the content and the target image. Secondly, we match the style to the target image using the texture level feature mapping of the style image. In order to do this, we access the feature maps of the convolution layers and use a transformation of these feature maps known as the Gram matrix. The Gram matrix is simply a covariance matrix, which is a representation of all the linear activations across all pairs of features, which highlights the texture or style of the image. Altogether, the loss function is as follows. Shown here, alpha and beta are weights of the content loss and style loss respectively and are hyperparameters. In our application of style transfer to clothes, the main hyperparameter that governs the strength of the style transfer is beta, which is normalized and can be adjusted according to the user's desire. As the main focus is tuning the styling, backpropagation is conducted onto the content image, as opposed to a separate target image, which increases the computational efficiency. Now, an important hyperparameter affecting the styling process is the type of feature map used to extract the style. As there is no model training taking place and what gets trained is the target image, we leverage the VGG19 model architecture using transfer learning and without having to worry about creating a CNN model from scratch. It is evident that the feature maps from the shallow convolutional blocks have more similarity to the overall style than the deeper convolutional blocks, which depicted more abstract representation of the style image. Therefore, the weighted contribution of the style extraction was higher for the shallow feature maps in our application. A user-adjustable parameter is the strength of the style transfer, which is seen as the blend or transparency of the style on the piece of clothing. This specific factor is controlled solely by beta of the loss equation. When the user wishes to increase or decrease this parameter using the user interface, what happens is the increase and decrease of the normalized beta parameter on a scale of 0 to 10. 0 being no style transferred and 10 being maximum possible strength of style transfer to the point where no significant changes can be seen. This was possible to achieve using the Adam optimizer's characteristics fast and smooth convergence, as well as accurate descent into global minima. RMS prop depicted oscillations due to large learning rates, and when the learning rate is small, the optimizer takes long in finding the local optima, infusing the content image with less texture from the style image. The level of detail and refinement of the style on the clothing is controlled by the number of epochs. More number of epochs, the more detailed the style transfer process is, as the loss keeps decreasing with more and more training to a point of 0, that there is no longer any useful information encoded in the error signal during back propagation. At this point, the clothing will have significant resemblance to the fine details of the style pattern. So in summary, the hyperparameter effects on the style transfer as follows.
For the task of segmentation, we use the clothing M dataset, which contains over 5,000 images of 20 types of clothing. As this dataset does not include segmented label, we created our own binarized labels using pixel intensity and thresholding. It can be observed that the data of interest is in the center of the frame and is unobstructed. Our first approach to create the data label is converting the RGB image into grayscale and then binarizing them using thresholding to separate the clothing from the background. Thresholding is calculated by creating a histogram of the grayscale images and then finding the two largest peaks which would represent the background and the clothing. However, this proves to be non-robust in case where there is no clear demarcation of the background and clothing. The second approach utilizes RGB segmentation of the apparel's pixel patch and then find the match of those RGB intensities similarities throughout the image. The patch size and the location are very crucial parameters because if the patch is located outside the apparel, then the algorithm will define background as the apparel. Still, this method was not entirely accurate, and about 20% of the total labels included some background noise and minor thresholding. It is evident that a better approach is required to create a mask using segmentation and is the main motivation towards a neural network-based segmentation using these created labels.
Now, using the clothing M dataset and the created labels, a unit-based neural network segmentation was utilized to obtain a clothing mask for style transfer. The unit-based architecture downsamples and then upsamples the image in such a way which can segment the clothing item and create a mask. The autoencoder bottleneck enables a receptive field of each individual pixel to essentially encapsulate the entire input image, and the residual connections help sustain the spatial correlations and the relative physical location of each individual pixel. The choice of the spatial resolution in downsampling was dependent on the computational runtime and convergence. Increasing complexity, such as adding more layers in the unit, yielded similar accuracy. Therefore, this simpler model was sufficient and it yielded a test accuracy of about 80%. However, this testing accuracy was not of major importance due to the nature of the dataset and the labels created, because there were a minority of the labels having depixelated or noisy labels, which are not the correct mask. This unit segmentation outputs a mask resembling the input image better than the label itself. And how does this happen? This happens based on the fact that the neural network not only creates a mask on the basis of pixel intensity, as in the previous method, but also on the basis of size and shape and other factors as shown here. This can be seen as the learnable upsampling of the transpose convolutions in the new unit structure, along with the downsampling, update the weights during backpropagation to create these feature activation maps.
Throughout the application, masking is done at two different instances. First, when the original target image is uploaded, and then after the style transference is completed. In the first scenario, we enter the original target image into the segmentation model, then we use the generated output to create two masks which are inversions of each other. The output will contain both positive and negative values. All the pixels which have positive values will be assigned with 1s, and all the negative pixels and zeros will be assigned with 0s. By going through each pixel while considering the above rule, an apparel mask will be created. Then by inverting this mask or by flipping 1s and 0s, another mask will be created which can then be used to extract the background. In here, we have utilized the previously mentioned masking with the style transfer image and the original target image to generate the final output. It can be clearly noticed how the texture of the output image varies according to the beta parameter and the number of epochs used. In here, you can see a few more of those examples. So far, the application was designed to style a single clothing item with an uniform background. We further improved this by enabling the user to add in images of them wearing the clothes so as to get an idea of what they would look like wearing them. In order to achieve this functionality, the iMaterialist fashion dataset was utilized with a pre-trained model in which the segmentation is achieved through a more sophisticated unit model. The segmentation model consists of 10 million parameters and a single output class. Testing the mobile app revealed that the segmentation functionality worked rather well, but is in need of a more robust segmentation process, such as semantic segmentation, to get a complete scene understanding of the images the user can potentially input.
So in conclusion, this project lays the groundwork for the styling and segmentation of clothing apparel functionality of a neural network-based mobile app. In future, we hope to improve furthermore using AI-based functionalities such as GANs to generate new types of clothing, classification to style multiple clothing items in a single image, get a list of similar looking products of a design between multiple users in the user's fashion e-commerce, transfer clothes between photos from a single image, also creating a personalized style store by learning the user's desires, users' design preferences, and predicting future fashion trends are few of the features we wish to achieve by combining multiple AI models, which we are yet to embark upon in future. Thank you.